What if I told you the future of quantum physics isn't cold, sterile, and locked in a vacuum chamber, but hot, chaotic, and buzzing with energy? Sounds crazy, right? For decades, scientists believed quantum behavior could only survive near absolute zero. But now, that belief is being shattered. The impossible is becoming possible, and it all starts with a cat that's both dead and alive. To understand how far we've come, let's quickly revisit the original experiment. Imagine a cat sealed inside a box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, the counter detects it, triggering the hammer to smash the vial, and the cat dies. If the atom doesn't decay, the cat lives. Quantum physics says that until you observe the system, the atom is both decayed and not decayed, so the cat is both dead and alive. Only once you open the box does the system collapse into one outcome. Schrödinger created this scenario not to suggest this was literally happening, but to highlight the absurdity and challenge of applying quantum rules to everyday objects. Now here's where things get wild. Traditionally, quantum superpositions like Schrödinger's cat have only been observed in extremely cold environments, close to absolute zero. That's because quantum states are fragile. Even tiny amounts of heat, thermal energy, can introduce noise that collapses the superposition. But what if we could observe Schrödinger-like superpositions at higher temperatures? What if the cat wasn't just alive and dead, but hot too? That's what scientists refer to as hot Schrödinger cat states. Superpositions created and maintained in systems that are more energetic, where thermal noise and environmental factors are harder to control. These hot cat states open the door to new questions. Can quantum coherence survive heat? Can entanglement hold up when things get messy? In quantum mechanics, temperature plays a huge role. At low temperatures, particles behave more predictably. They can exist in superposition for longer because there's less interference. But when you add heat, when particles gain energy, they become more chaotic, more interactive, more difficult to isolate. This is what makes hot quantum states so difficult to study. And it's why, for decades, scientists avoided it. It was just too noisy. Yet if we could harness quantum effects in hot systems, we could potentially build quantum devices that don't require extreme cooling, bringing us a giant leap closer to practical quantum computing and communication. In 2025, researchers at the University of Innsbruck in Austria accomplished what many thought was impossible. They successfully created hot Schrödinger cat states in a laboratory setting. Using a superconducting microwave resonator, the team generated quantum superpositions at temperatures up to 1.8 Kelvin. That's about 60 times hotter than what's typically used in quantum experiments. And yet, the system maintained coherence long enough to be observed and studied. This was the first clear demonstration that quantum cat states can exist in more thermally energetic environments. It proved that heat doesn't automatically destroy quantum behavior, and that opens up a whole new frontier for quantum research. Entanglement is already one of the most bizarre and powerful phenomena in physics. Two particles become so linked that changing one instantly affects the other, no matter how far apart they are. But what happens when entangled particles are part of a hot quantum system? In hot Schrödinger cat states, entanglement gets more complex. Particles may shift between energy levels, respond to temperature changes, or exhibit unexpected quantum correlations. Instead of collapsing, some entangled systems adapt, creating new kinds of hybrid states. Researchers are now testing how entanglement behaves under these conditions, and whether heat can be used as a control mechanism rather than just a disruptive force. The ability to stabilize hot Schrödinger cat states could lead to breakthroughs across multiple fields. Quantum computers that don't require expensive, ultra-cold environments. Quantum sensors that work in practical settings like space or hospitals. Quantum networks that are more robust, reliable, and scalable. This is more than a curiosity. It's a step toward making quantum technology work outside the lab and in the real world. What started as a quirky thought experiment with a cat in a box has become one of the most exciting areas in quantum physics. By proving that quantum states can survive at higher temperatures, the Innsbruck experiment showed us that Schrödinger's cat doesn't need to be cold and fragile. It can be hot, energetic, and still very much alive and dead. Hot Schrödinger cat states remind us that the quantum world is still full of surprises. And as researchers push these boundaries, we may find that the key to building the future of quantum technology is just letting things heat up a little. If you enjoyed this, don't forget to like, subscribe, and hit the bell so you never miss an update. Thanks for watching and stay curious. Until next time.